Let me just start by saying that the two things I dread the most when I'm giving a talk. One is to follow Martin Rees, the other one is to follow Jim Peebles. And anyway, so I got the second today. Nevertheless, I'm going to tell you about the cosmic dark matter, where and what is it. This is the first of the Ogden 5 questions. So when the Ogden Centre was set up, Peter formulated these 5 questions. Now, I'm slightly embarrassed to say that 20 years later we haven't answered any of those. However, as you will see, we have made quite a few inroads in trying to understand at least what the questions mean and how we should go about trying to address them. But the questions were very hard, I must confess. So one of the big surprises of physics and cosmology is the realization that the contents of our universe are really truly bizarre. Jim already talked about this a bit, so I'm just going to do it in a succinct fashion by showing you a pie diagram. So we now know that only the ordinary matter, what Jim was calling the baryons, this ordinary matter, the matter that we see in the periodic table, what Judith Howard chemist studies, that matter, what we call ordinary matter, makes up only about 4% of what the universe contains. About 24% is the dark matter that Jim told us about in 1982. This is dark matter that, as the name indicates, is dark. It doesn't shine at any wavelength or not most of the time, of the electromagnetic spectrum. And then the lion's share of the universe is provided by this dark energy that makes up over 70% of what the universe contains. And the simplest version of dark energy is the cosmological constant that Jim told us all about. Now, the reality is that we really only understand the 4%. We really don't quite know what the dark matter or the dark energy are. But we're advancing in trying to answer these questions, and I'm going to focus here today just on dark matter. I'm going to let the much harder problem of dark energy, I would let my colleague Saunak over there tell you about that. He's a early career researcher, although I must say that what I work on is so exciting that every day I come in to work, I feel like an early career researcher. But when I look in the mirror, I realize that's not the case anymore. But nevertheless, so we cannot see the dark matter, so how do we know it's there? And Jim already told us about it, and we know it is there thanks to the wonderful laws of physics. And in particular, in this case, is Newton's law of physics that tells us that matter produces gravity, gravity makes things move. And that's exactly why an apple fell on Newton's head. And that's also the reason why we can infer matter just by looking at the way in which things move. So for example, if we know how the planets move around the sun, and we know the distances to the sun, we can very easily infer the mass of the sun. So using that very same principle, these beautiful laws of gravity from Newton, astronomers inferred already many decades ago that there had to be dark matter around galaxies simply because the velocity at which stars go round and round the sun, around the center of the galaxy, is just too large for that velocity to be explained by the gravity of the matter that you can see in the form of stars and gas clouds. And so the inference was that there had to be something else beyond what you can see. Now, the other day, a few years ago, I was in London worrying about one delicate aspect of this. I was really lucky that I came across Newton. Yes, Isaac Newton in his model incarnation. He is Newton. Look, the nose is the same. It's not just the hair. The eyes are the same. So Newton reincarnated as a musician, and I don't know if the young people here recognize who he is. It's Brian May. Now, what you might not know is that Brian May is an astronomer. I know him because he's an astronomer, not because he is a guitarist. And Jim, talk about monetizing astronomy. So he managed to do it very well. And he actually told me once that he wonders what his career would have been like if he had stayed in astronomy. Anyway, so the picture you should have of galaxies is really a little pool of light, stars and gas clouds embedded in a much bigger clump of dark matter, which we imaginatively call a halo of dark matter. It's not really a halo, it's a centrally concentrated lump of dark matter, and the galaxies sit there in the middle. Now, and it is that dark matter that keeps the galaxy in place, as I indicated. That's just one way to prove that, or give evidence for the existence of dark matter. There's another, in a way, very elegant and subtle way, and that is by analyzing images like this from the Hubble Space Telescope. So what you see here is a cluster of galaxies. Many of these are normal galaxies, but if you look closely enough, you will see that there are also these bizarre arc-like features all over the place. And these are also galaxies, strange-looking galaxies. The reason they look so strange is because these galaxies are a long way behind the galaxy cluster, and the light, as it passes through the mass concentration of the galaxy cluster, gets deflected. And you know that if light gets deflected, then the image of the object that produced the light gets distorted. So these so-called gravitational arcs are nothing other than distorted images of galaxies a long way behind the cluster whose light has been affected by the, there's somebody calling me, I hope it's not Brian May. No. Anyway, so it wasn't Brian May, whose light has been affected by the concentration of mass in that cluster. And this is something that Einstein predicted many, many years ago. Here is the way in which people used to do science in 1917, is it? 13. Here you see a light ray, in this case being deflected as it goes near a star by the gravitational field produced by this gravitating body. In this case, a star. In our case, it is in fact a galaxy cluster. Now we've done an experiment. See if this works. I don't know if the movies will work. It's not my computer. So what you see here is an image called the Hubble Deep Field. It's the deepest image that humans have ever made. So the light that you see, especially from the small galaxies here, these galaxies are so distant that the light you see has been traveling for most of the age of the universe. So we're going to use this as a tapestry. It's just the background. And then the experiment consists of blowing or growing, if you like, a lump of dark matter. It's going to get more and more massive, and you see the effect of that growing lump on the background galaxies. So, that's what I feared. My movies don't work, unfortunately. So we had to, in order to be able to do the Zoom, we had to move my talk from my computer to this one, and the movies didn't come with it. But I can tell you what it would look like if we had done the experiment. So this is simply solving Einstein's equations to see how the light would be affected by this growing lump of dark matter. And what you would see is all the galaxy images stretching into arcs exactly like the arcs that we saw in the galaxy cluster. So we understand exactly what this phenomenon is. Many people here at Durham study gravitational lensing, and with that we can, I wonder, no, it's not going to work. It looked as though it was trying to, no? No, I don't think it's going to. Let me give it one last time. I don't think. No, I don't think the movie's transferred. It doesn't matter. And so, because we understand this phenomenon very well, we can use it to weigh to basically weigh the cluster, calculate how much mass is needed to produce these distortions. And the answer is that there's about 10 times more of this dark stuff than there is in material that we can actually see. So that is one of these measurements that Jim referred to that really establish quite conclusively and in a compelling way the existence of dark matter. So, what have I told you so far? We know dark matter exists for two reasons. Because one is the rotation velocity of galaxies, of stars in galaxies, and the other one is this phenomenon of gravitational lensing. Now, so what is the dark matter? So I haven't got the answer yet, but I can tell you what we think it is. Here's a picture of the Big Bang, a cartoon, no doubt drawn by particle physicists, because most of the is not in the correct proportions. Most of the diagram is occupied by the particle physics aspect of the universe, which, however, only lasts about 350,000 years. It's also here it is the Big Bang, and here we are 13.7 billion years later, wondering about what the universe has given us. Now, so the current idea is that the dark matter is some form of elementary particle that was created very soon after the Big Bang, maybe 10 to the minus 10 seconds after the Big Bang, some form of elementary particle, different, as I said, from ordinary matter. And the best bet that we have, in fact, some of that goes back to this man sitting here, something called cold dark matter. That is the best, this is John Ellis, who will talk tonight. The best bet we have is that the dark matter is a particular type of elementary particle known as cold dark matter. Now, so why is the dark matter so interesting? We have a whole institute that most of the people, or many of the people there, worry about dark matter. So why is it so important? Well, one reason, of course, we want to know what the universe is made of. That's all self-evident. But it's a more subtle reason, and that is, I think Jim suggested this, that the dark matter is responsible for everything we see in the universe. So the dark matter is responsible for all the structures we see, galaxies, eventually even stars, planets, and people. If we didn't have dark matter, our universe wouldn't look anything like it does today. So let me explain to you how this happens. So where do the galaxies come from? And I will show you that galaxies started, as Jim indicated, very early on, small perturbations in the universe, which were then amplified by the gravity of the dark matter. So here is, again, the picture of the Big Bang. And this story begins very soon after the Big Bang itself, a decimal point and 35 zeros, and then 1, that fraction of a second, 10 to the minus 35 seconds after the Big Bang, when the universe, for reasons we don't fully understand, happened to be born in a slightly unstable state, and the way it tried to become stable, to stabilize itself, was expanding very rapidly during a period known as cosmic inflation, which is shown here as this in this part of the diagram. Now, inflation is driven by quantum processes, and one of the main lessons of quantum physics is that in the quantum world, everything is fluctuating in the form of things called quantum fluctuations. Now, these quantum fluctuations during inflation get stretched and become imprinted as small perturbations in the energy density of the universe at these very early times. So the universe goes from being uniform to being speckled with small irregularities where the density, the temperature, the pressure in one place are slightly different from those quantities in another place. So the proposition of modern cosmology, which is quite bold, is that everything we see in the universe today was once one of these quantum fluctuations from inflation, which is quite something to say. And the wonder of physics is that this, it's a legal statement in Jim's language. This can be tested, and I will show you how we test it experimentally. So once these quantum fluctuations have been established, then they get amplified by the gravity of the dark matter. And then when the universe is 350,000 years old, which if we scale it to a human life would be the equivalent of 1 day old, the universe, that's when the hydrogen atoms that Jim was telling us about form, and then the radiation that was trapped or scattering with electrons beforehand is now free to escape, and it brings us news about what was going on in the universe at this very early time. Now, Jim almost showed you this plot. This is a picture of the temperature of this radiation, microwave background radiation. It's around us, but you project it in order to put it on the screen onto one plane. So it's a picture of the temperature of this microwave background radiation. And as you can see, it's not uniform. It has hot and cold spots. And these hot and cold spots, if the theory is correct, is nothing other than a reflection of these quantum fluctuations from inflation. So this is an amazing picture to look at. Here, in fact, not this picture, but the previous one, from the COBE satellite was first published. George Smoot, who got the Nobel Prize, he made a mistake. He said this is like looking at the face of God. I don't think that's quite true, but nevertheless, it was a big breakthrough. So now here is what I regard as the most glorious plot of my scientific career, and I had nothing to do with it. What's plotted here is the temperature difference between 2 points on this map as a function of how separated they are. The green line is Jim Peebles' 1982 curve. That's the green line. The dots are the measurements of this European satellite called Planck. Now, and the agreement couldn't be better. So to me, it's always been one of the greatest mysteries that why is it that in this galaxy, it's like many other galaxies, there's a species of living creature has evolved that on the one hand has the ability to make theories that describe the conditions that prevail at the very beginning of the universe. That's Jim's green line. And this same species also has the ability to build machines that they launch out of the planet capable of making these incredibly delicate measurements because the signal here is 1 part in 100,000, as Jim explained. So this is how we have confidence in a theory of modern cosmology. Now, so what happens then between the initial conditions and today's universe? Well, that's a much simpler problem, believe it or not, even though this is only 350,000 years after the Big Bang. Now we are 13.7 billion years later, because the physics is very well understood. It's not that easy to solve the equation, but it's not possible unless you program a big computer to solve the equations of physics. And that's what the Institute for Computational Cosmology does. That's why we call an Institute of Computational Cosmology, because we spend our time computing, solving the equations of physics that allow us to go from the very early time to the present day. So how do you make a universe in a computer? And I would say this is a new way of doing science. So traditionally we had theory and experiment, and over the last few decades we now have this new tool of science, which is computing and simulations that of course is used not just in cosmology, it's used in climate change and in biology and in many other disciplines. So we know the initial conditions. You make some assumption about the nature of the dark matter, say that it's called dark matter, and then the rest is just solving equations that we know and love, and we know how to solve them. If we are interested just in dark matter, we just need to solve these two equations. If we're interested in things like stars and gas clouds and so on, it probably gets more complicated, but it can still be solved. You program the computer to solve these equations, and then you come back later and see what came out of that. Now, normally I would show you a movie, which I'm not going to be able to show you. Oh, I am able to show you. You see here, what you see here is the formation of this lump of dark matter in which the Milky Way sits. It started, well, it's too much light, but these very small fluctuations that you could see there, these quantum fluctuations that I'm talking about, and you see how they get amplified by the force of gravity. And very soon, this universe is only 160 million years after the Big Bang. Very soon, just through gravity acting on dark matter, the universe acquires this amazingly beautiful pattern known as the cosmic web of intersecting filaments and low-density regions. And you really see gravity in action. So in a minute, you see these objects will stop expanding and will come back attracted by this lump of mass that's growing here, which gets bigger as it attracts matter. And then it attracts even more matter because it's even bigger. It's an instability, and this is how the clumps of dark matter in which galaxies sit form. And what you see here is really only the solution of these equations that I told you about before. And then I'll stop the movie here, but then a galaxy would form in there. So here is, where is the dark matter? Well, it's everywhere. And if you were able to travel at many times the speed of light, and you were able to see the dark matter, this is what you would see. You would see this pattern, and it all came from quantum fluctuations. That's what's absolutely amazing. It all came from these quantum fluctuations of inflation, and you end up with this very rich tapestry where the dark matter is distributed. Again, this is called the cosmic web. Now, so that is the easy part of the problem. The complicated part of the problem is to understand, or before I tell you about that, I would say, Peter, that we haven't answered fully the question, but what the question we have answered, we know everything we need to know about the properties of the dark matter distribution if it is cold dark matter. All right, I will stop in a second. I'll do like Jim. Stop, Jim. So if the correct theory is cold dark matter, we've solved that problem, and we know exactly what the dark matter is doing on all scales. And I'll show you a plot here from we published in Nature a couple of years ago. Saunak is one of the authors. Now, this plot that is very impressive. It's just a straight line. So what's plotted? Most of the straight line with some curvature here. So what's plotted here is the number of dark matter clumps, of dark matter halos as a function of mass. So well, what's the big deal? The big deal is when you look at the units. So these are powers of 10, and these are 25 orders of magnitude, 1 and 25 zeros. So that's the number. It ranges from that to that. That's the mass. This is the mass of the Earth. This is the mass of the galaxy cluster. So we have now been able to essentially calculate how many halos of all masses, from the mass of the Earth all the way to the mass of a galaxy cluster, how many there are in our universe. And it's in that sense that we have completely solved the problem of where is the dark matter. Now, just to finish off, in the last few years, there's been quite a lot of progress in being able to simulate not just the dark matter, but also the baryons, the ordinary matter that makes up the galaxies. So here is the result of a simulation done here in Durham, a collaboration called the Eagle collaboration. And here you see evolution in time. This is the dark matter we saw before, but in a minute we're going to cut to the ordinary matter, to the baryons, the gas. And the gas you see now here. And the gas is following the gravity of the dark matter. So where there were lumps of dark matter, there are lumps of gas as well, but the gas can dissipate energy. And everything in the universe is spinning. Jim told us why, and Fred Hoyle some years ago. And you see this gas that is able to lose energy, then settling into a spinning disk that looks a lot like the galaxies. These are the stars in our simulation. And we'll now continue. We'll stop for a second to admire. And this came just out of these quantum fluctuations. There's no image processing. There's nothing. It's just physics and the initial conditions from inflation. And of course, it's happening not just where this galaxy is. It's happening everywhere in the universe. And as we will see in a second. That's the stars. Very nice thin disk with very small bulge. And we're going to discuss this with Jim tomorrow. And here is what's going on everywhere in the universe. So I ran out of time, so I just want to almost leave you with this picture, a gallery of galaxies. The astronomers here would think, oh, this came out of the Hubble Atlas of real galaxies. No, it came out of our computer. Paula, I'm done. And so let me just skip through some of these slides that I didn't have time to talk about and just go, just go to my conclusions. Ultimately, the search of dark matter is part of experimental physics. I don't know if you've ever seen an experimental physicist about. This is what they look like. And the dark matter, there are various ways in which one might detect dark matter. One of them is just capturing it directly in a laboratory. These experiments happen in mines. The other one is to make it at the LHC. And there's another exotic way which I'm not going to describe. I just want to finish off with two comments. All these efforts are international. Just like our institute and the Ogden Centre are international, all these efforts involve many countries around the world. And I want to leave you with this last picture as Peter Ogden, who was a theorist, now as an experimental physicist, here visiting the Bowlby mine, where the British experiment for dark matter was being conducted. This is many years ago. Tim Simmons is there as well. So I'll just leave you then with the statement that the identity of the dark matter is, of course, one of the great mysteries of modern science. And it's not yet solved, but we've made great progress towards trying to answer this question: where, where, and how. Now, where is the dark matter? What is it? And that was it, wasn't it? And I'll finish here.
Thank you, Carlos. He knows he's in trouble when I draw myself up to my full 4 foot 11 and a half inches tall. So I think we have time for maybe one question. Yes, we have a question up there. If you'd like to go. Sometime we need a question down here somewhere.
Right, it's a very good question. So I think if I heard you correctly, the question is, if you do look at a galaxy like the Milky Way, it's flat, whereas the dark matter is distributed as a kind of spheroid, and almost spherically. And the reason is, the reason is that the dark matter doesn't interact through any other forces other than gravity. If we're lucky, it will interact very weakly with mass, but it doesn't interact strongly. And so it can only interact by gravity. Gravity is an isotropic force, so any object that forms by gravity tends to be spherical or spheroidal. The ordinary matter, on the other hand, that can interact in many other ways, and in particular it can cool. So the dark matter can emit radiation. The ordinary matter can emit radiation that's called dissipation. That's just because of atomic processes of various kinds that allow this ordinary matter to lose energy. And that's why it can then settle onto a disk. So it settles onto a disk as it loses energy due to these atomic processes and the so-called dissipation. And because it's spinning, and for reasons we understand why things spin, then if you have a gas cloud that can cool by radiative processes and is spinning, it will settle onto a disk. And then the disk fragments into stars, and that's the basic idea of how spiral galaxies form and why their configuration is so different from that of the dark matter.
Okay, so let's thank Carlos again. Thank you, Carlos.